Dear students, in this video we will discuss about the Zeeman effect. That is, here in the Zeeman effect we will discuss what happens to an atom when it is in the magnetic field and how the different energy levels get split when magnetic fields act on an atom. So here the main question is that what happens? What happens to an atom when when it is in the magnetic field, in the magnetic field. So in order to find out the impact of the magnetic field on an atoms, so here we will discuss the two important things when we consider the atom within the magnetic fields. First thing I will tell you here is that we can consider the atom like a tiny magnet or which has a magnetic dipole, which act as a magnetic dipole in an external magnetic field. In an external magnetic field. So the atom will behave as a magnetic dipole when we apply the magnetic field. So here we will discuss the two important phenomena. The first is about first thing will be the potential energy, and the second thing which we will discuss is about torque. So let's suppose that we have a magnetic field in this direction. So this is the magnetic field. This one is the magnetic field. We can represent the magnetic field by the B. B represents the magnetic field. Now if an atom which acts as a magnetic dipole, it is in the magnetic field, and here it has magnetic moment mu, and magnetic moment mu of electron makes an angle theta with magnet in the direction of magnetic field with the magnetic field line. So first here I will discuss about the potential energy in an external magnetic field. This is the B is the external magnetic field here. Magnetic field. So the magnetic dipole has the potential energy. So the magnetic dipole has potential energy, has potential energy, and we can represent the potential energy by um. This is the potential energy within the magnetic field. So here the potential energy depends on the magnitude and orientation of magnetic moment mu. It depends on the magnitude and orientation of magnetic field, of magnetic moment mu. Okay, so the magnetic moment as atom which acts as a magnetic dipole when placed in external magnetic field, its magnetic moment mu try to orient themselves in the direction of magnetic fields by making an angle theta with the field. So it has potential energy which can be represented by and potential energy depends on the magnitude, that what is the amount of this magnetic moment, and its orientation, and that is the direction of magnetic moment, that is how magnetic moment turns in the presence of magnetic field. Now the next thing is to find out the torque on magnetic dipole. Torque on magnetic dipole in an external magnetic field. Here the torque can be represented by tau, as we can redraw. These are the magnetic field lines, and so this is the magnetic field, and when we place the magnetic dipole within the magnetic field, it has the magnetic moment mu and makes an angle theta with the B. So the torque will be equals to the mu B sine theta. It will be equals to the mu B sine theta. Here we can see that theta is the angle between mu and B. Mu magnetic moment and B is the magnetic field. So the tau is maximum. When it is the maximum, tau will be the maximum. Here you can see that when the theta is equals to 90 degree, as sine 90 is equal to 1. So the torque will be the maximum when theta is equal to 90 degree, or you can say that when magnetic dipole is perpendicular to the field. Perpendicular to the field. Then the value of tau is maximum. And tau, when tau is the minimum, tau has the minimum value. It will be the minimum. When it is the minimum, it has minimum value when theta is equals to 0. That is when dipole align parallel to the magnetic field, is in the parallel direction to magnetic field B. So now we will discuss the potential energy. That what is the potential energy of magnetic dipole within the magnetic field. Now we will find the potential energy which can be represented by UM, that is the potential energy of magnetic dipole within magnetic field. So here to find out the potential energy UM, we consider some reference configuration in which we consider the UM is equal to 0. UM will be 0 in the configuration, or in the reference. We can consider that in the reference configuration, which we consider our starting point, then the UM will be equal to 0. Why we consider the UM equals to 0 in our reference configuration? Because we consider only change in potential energy. Change in potential energy. Okay. So here we consider the only change in potential energy, because only the change in potential energy can be measured experimentally. So we consider our reference configuration in which the potential energy is equals to 0. What will be our reference point where UM is equals to 0? UM will be equals to, we consider the UM is equal to 0 at when theta is equal to pi by 2. That is when mu is perpendicular to the B. That is when mu points in the perpendicular to B. That is, this one is the B field. Again I can draw it. This is the B, and we consider when mu points perpendicular in the B direction. So theta is the 90 degrees. So this is our reference configuration. So at any other orientation of the mu, as the magnetic field act on the mu, you know that mu torque act on the magnetic moments, and magnetic moments try to align itself along the magnetic field. So its reference configuration, if theta is equal to pi by 2, will be equals to 0. So at any other orientation, it is equals to the external work done or done to rotate the dipole from theta is equal to dipole. As you know that torque act on the magnetic dipole moment, it means that, so as you know that the torque has turning effect. Torque means that turning effect, and torque, when torque act on the magnetic dipole moment mu, it means that external work done to rotate the dipole from theta is equals to pi by 2 to at any other configuration. So to any other configuration theta. And so the work done potential energy is equals to the work done from theta is equals to pi by 2 to theta and to is equal to tau d theta. So here by putting the value of the tau, we can write it like this one, pi by 2 to theta, tau is equal to mu b sine of theta d theta, and it will be equals to minus mu b cos of theta, and this one is the equation 2. You can say that potential energy is equals to minus mu b cos of theta. So mu and b are parallel to each other, then will be equals to minus mu b. So minus mu b, when that mu and b will be parallel when theta is equal to 0. When theta is equal to 0, cos of 0 is equals to 1 and potential energy will be equals to minus mu b. This is the minimum. This is the minimum potential energy of magnetic dipole. That is the magnetic magnetic dipole tend to align itself along the direction of magnetic field. When it is in the direction of magnetic field or parallel to the magnetic field, then at that moment potential energy will be minimum, and that minimum potential energy will be equals to minus mu b, because cos of theta, here cos of 0 is equals to 1 because theta is the 0 when mu and b are parallel to each other. Now we will consider the magnetic moment of electron in an hydrogen atom. Okay, now we will consider the hydrogen atom. As you know that hydrogen atom has only the one electron. So here we will consider the magnetic moment of electron within the hydrogen atom. As the magnetic moment of orbiting electron in a hydrogen atom depends on the angular momentum. It depends on angular momentum. Angular momentum decides the magnetic moment of electron of hydrogen atom. That is the magnitude and orientation of L. Magnitude and its orientation. And orientation of angular momentum of electron in an hydrogen atom will decide the extent of magnetic contribution to the total energy of an atom. That is when atom is in the magnetic field, when atom in a magnetic field. That is when atom is in the magnetic field, then magnetic field impact the orientation and magnitude of, has its impact on the magnitude and orientation of angular momentum. So the orientation and and its magnitude of angular momentum will tell us the extent of magnetic contribution to the total energy of an atom when it is in the magnetic field. So here we can consider the electron, orbiting electron, as a current loop. Okay, we can consider the orbiting electron as a current loop. So it has its magnetic moment mu will be equals to the I into A. Here, what is the I? I is the current in the while loop, and A is the area. A represents the area of loop. Okay, and I, as the electron is orbiting the wire, so the I will be equals to the minus EF, as E is the charge on the electron, minus E is the charge on the electron, and F is the F represents the rate of revolution, that is the rate of revolution per second, which is equals to the current. That is how many revolution electron makes around this loop in 1 second. So it's a I will be equals to the charge on the electron, and F, which represents the rate of revolution per second, I will be equals to the minus EF. And A, what will be the A? A will be equals to the pi r square, because it is the area of the current loop, because here the current loop is we consider the loop or as a current loop as a wire, that is its area of cross section will be equals to the pi r square. So what will be the mu? By putting the value of I and A, it will be equals to the minus EF pi r square. So we can consider it as in equation 3. As mu is equal to minus EF pi r square. Now we will consider the linear speed of electron. Linear speed of an electron. Now the speed of electron, we know that formula for the speed is equal to V is equal to S over T, and 1 over T will be equal to the F, so it will be equal to the V is equal to S F, and we know that S is the distance. So here is distance is the circumference of that current loop, which will be equals to the 2 pi r into F. So V will be equals to the 2 pi r F. Now the angular momentum L is mvr. Now putting the value of V from equation A into equation B. So L will be equals to the m 2 pi r F into r, and so the angular momentum will be equals to L will be equals to the 2 pi m F r square. So here from here we can separate the value of r square. So r square will be equals to the L over 2m L over 2m pi F. So this is our equation number 4. So we will insert the equation 4 value of r square into equation 3. Inserting value of r square in equation 3. So we will get mu will be equals to minus EF pi into L divided by 2 pi mf, and so it will be equals to, here we will get F will be cancelled out, and as well as the pi will be cancelled out. So the remaining quantity will be equals to E minus E divided by 2m into L. Okay, so mu will be equals to minus E divided by 2m into L. So this is our equation number 5. So here we can see that the quantity minus E divided by 2m. This is the charge. It represents the charge and mass ratio of electron. Charge and mass ratio of electron in an hydrogen atom. And this is called as the gyromagnetic ratio. Okay, and negative sign here represents that the magnetic moments mu and L point in opposite direction. In opposite direction. So this negative sign indicates that mu and L are in the opposite direction due to the negative charge on an electron. Now we will discuss the potential energy of hydrogen atom in magnetic field. In magnetic field. Okay, so now the magnetic, we know that the magnetic moment, as we have already discussed, that is mu m is equals to minus E divided by 2m into L. Mu is equal to minus E divided by 2m into L. Now magnetic, you know that the potential energy is equals to, we have already found this equation, minus mu b cos of theta. So now putting the value of mu, this value of mu in this equation. So the potential energy of atom in magnetic field will be equals to minus E divided by 2m into LB cos of theta, and it will be equals to the E by 2m into LB cos of theta. As the angle theta between, this is the angle theta is the, this between L and Z direction of L. It is between L and Z direction of L, that is LZ. That is, as we know that the angular momentum L is quantized. When it is the quantized, it means that its magnitude and orientation, both are quantized. So when its magnitude and orientation both are quantized, it means that it can only take the specific values. Not all values are possible, rather the angular momentum will orient themselves only in the specific orientations. And so we know that the value of angular momentum is equals to L into L plus 1 under root h cut. Here L is the orbital angular momentum quantum number. Now let us consider the angular momentum direction LZ, that is the Z component of angular momentum quantum number. As we know that angular momentum is, this is the Z direction, as we know that the angular momentum is quantized. So it is quantized is in its magnitude and direction. So it can have only the specific orientation, so the value of LZ will be equal to ML h cut. Now what is the L? ML. ML represents the magnetic quantum number. Magnetic quantum number. So it means that within the magnetic field, the angular momentum can take only the specific value, and this magnetic quantum number tells us about the orientation of angular momentum in space. Tells us about the orientation of angular momentum in space, or in other words, there is another terminology which is called as space quantization. Space quantization. So due to the fact that the angular momentum is quantized in magnitude and direction, so the angular momentum quantum number magnetic it is also called as the magnetic orbital quantum number, which tells us the orientation of angular momentum in the space. So it means that within the magnetic field, angular momentum can take only the specific direction, not all orientations are possible. For example, for L is equal to 1, if L is equal to 1, then ML has the values for any value of L. It has the value minus L through 0 to plus L. So for L is equal to 1, ML can have the values 0 and plus minus 1. Let's suppose this one is the LZ, Z direction of orbital angular momentum. Then for L is equal to 1, orbital quantum number L is equal to 1, then it can have the 3 orientation. This one for ML is equal to 0. Let's suppose this one is the ML is equal to 1 and ML is equal to minus 1. So it can have these specific orientation as LZ is equal to ML h cut. So this the ML has its projection in the direction of over the LZ, and so this LZ will be equal to ML h cut, and so these are its possible orientation. This will be equals to minus h cut, 0, and we have the plus h cut. So it means that if we consider this one, it means that cos theta will be equals to ML h cut divided by L. So if this one is the L and here this is the ML h cut, then cos theta will be equals to ML h cut. This one is the angle theta. If we consider here, this one is the angle theta between L and LZ. Theta is the angle here between L and LZ. So cos theta will be equals to, and LZ is equals to ML h cut. So cos theta basically equals to LZ divided by L, and LZ is equals to ML h cut divided by L. So by putting value of L which is equal to L into L plus 1 under root h cut, cos theta will be equals to ML h cut divided by L into L plus 1 under root h cut. Now using this value of cos of theta in equation of the potential energy. So the potential energy, as we know, that it is equals to E by 2m into LB cos of theta. So putting the value of cos of theta and L, the potential energy will be equals to, it will be equals to E by 2m into L into L plus 1 under root h cut into ml h cut divided by L into L plus 1 under root h cut into B. So these values will cancel out each other, then potential energy then will be equals to, it will be equal to E h cut divided by 2m into ml B. Now we have this one quantity. So here I can rewrite the equation for potential energy is equals to E h cut by 2m into ml B. So here the quantity E h cut by 2m. This quantity is called as Bohr magneton, and value of the Bohr magneton, which can be represented by mu b, its value is 9.274 into 10 to raise power minus 24 joule per Tesla, or it can be equals to 5.788 into 10 to raise power minus 5 electron volt. So these are the values of Bohr magneton, which is equals to E h cut by 2m. So the potential energy will be equals to mu b ml into B. So now we will see, or we will consider the energy of particular state in the magnetic field, that how the potential energy of specific state or specific shell within this, what will be its energy within the magnetic field, and how what is the impact of the magnetic field on different electronic state. So we consider here the energy of particular state within magnetic field, or B field. So the energy of any state depends on the two things. Number one, it depends on the principal quantum number, and secondly, it depends on the magnetic quantum number. Which can be represented by ml, and principal quantum number can be represented by n. So here, as we have already discussed, the equation for the potential energy, which is equals to mu b, which is the Bohr magneton, ml b. So here ml is the magnetic orbital quantum number, or it tells us the behavior of the atom within the, what will be the energy of atom within the magnetic field. Now we are talking about the energy of particular state. So the energy of particular state depends on the principal quantum number and magnetic quantum number. So it tells us that how the energy of any particular state change within the magnetic field as as the state of the total quantum number, which can be represented by principal quantum number n. So the n split into several states in the presence of magnetic field. Split into several states in magnetic field. When we apply the magnetic field, then this total state of the total quantum number or principal quantum number and will split into the several substate which are called as several states, which are also called as the subshell or substates. So these substates of an atom is in the magnetic field, in the presence of magnetic field, and their energies are very slightly more or less than their original state. So their energies are more likely or slightly less than less than or more than the original state. Original state. So and here we can say that the phenomena of the splitting, this phenomena of the of splitting of spectral line in magnetic field or in the presence of B field. So this phenomena is known as, we called it Zeeman effect. Whenever we apply the magnetic field, there is the splitting in the principal state or n, which can be represented by n, into the several substate which are slightly more or less than in energy than their original state. This phenomena of splitting is known as Zeeman effect. So the Zeeman effect, we can also say that it is the confirmation of space quantization. Zeeman effect represents the confirmation of space quantization. As we have already discussed that space quantization, uh, which can be explained by ML, magnetic quantum number, that is space quantization, tells us about the possible orientation of orbital angular momentum L in space. Okay, so this is the space quantization. So the phenomena of the splitting of spectral line into the several line, and every line has its own specific orientation in the magnetic field. So this Zeeman effect is also called as the confirmation of space quantization. Now ML, which is the magnetic quantum number, it can have only the specific orientation, or it can have the only specific values which explain the orientation of orbital angular momentum in the space. So it can have only 2L plus 1 possible values. So its varies from plus L through 0 to minus L. So it can have only two possible values, or there are only two L plus 1 orientations are possible for any orbital quantum number. So we can say that So the state of given orbital quantum number L can split into the two L plus 1 state that differ by a factor of mu b into b. As we have already know the equation of potential energy, which is equals to mu b ml into b. So as ml tells us about the splitting of the space for any of states for any value of orbital quantum number. So these splitting in states can be differ by a factor of mu naught b. So mu naught b, these states will be mu naught b either will be less than in energy or can be in the more than the energy of their original state. As we have already explained that the Zeeman effect tells us about the splitting in the presence of magnetic field. So the Zeeman effect in Zeeman effect we explain the splitting as uh, there are the two different types of the Zeeman effect. First is the normal Zeeman effect. Normal Zeeman effect, and secondly there is the anomalous Zeeman effect. Okay, and anomalous Zeeman effect is little bit complicated because here we also consider the spin and interaction of spin or spin and orbit, that is spin orbit coupling, and we also take into account into for only those spectral line for which we have the for which we have the half spins. Mm. Half spin states we consider only for those atoms in which we have the half spin state, that is the states are not fully filled. Either these can there are the states which are the partially filled either with the electron with the spin up state or either with the electron with the spin down state. So we for these type of the atom to explain the spectrum of these atoms within the magnetic field, we use the anomalous Zeeman effect, and here we consider the spin and orbital angular momentum interaction. And for anomalous Zeeman effect, here we consider only the orbital angular momentum. As we know that the all types of splitting are not possible. So here we consider first we will consider the normal Zeeman effect. So first we will consider normal Zeeman effect. So for the case of normal Zeeman effect here, not all splitting, as I have already told you that not all splitting are possible, as there is the selection rule. There are the selection rule which tells us that which of the transitions are possible and which one are forbidden. And selection rule for ml orbital quantum number is that delta ml, it should be either equals to 0 or it should be equals to plus minus 1. So it means that whenever there is the transition between the two states of different orbital quantum number, and these should obey this selection rule for delta ml. So only those transition are possible are called as the allowed transition, which will obey this selection rule for the orbital quantum number. For the orbital quantum number differ only by a 0 or by plus minus, or it should have the plus minus 1 values. Only those transitions will be possible. All other transitions will be called as the forbidden transition. So here we expect the spectral line from a transition between the two states of different orbital quantum number to split only into three components. Okay, in normal Zeeman affair, so the spectral line from one spectral line which is the result of transition between the two states, that is, this one is the one state, L is equal to 0 to L is equal to 1. So for in the presence of magnetic field, we can observe only the three components. There will be the three different splitting will be possible for the normal Zeeman effect. Now we will see that how these three transitions are the only possible transition or the allowed transition for in the case of normal Zeeman effect. We observe the normal Zeeman effect. Normal Zeeman effect. Normal Zeeman effect is possible only for a system with closed shell. System with closed shell. This is the basic difference between the anomalous Zeeman effect and normal Zeeman effect. As I have already told you that the anomalous Zeeman effect occurs in those atoms in which we have the half-filled shell or with the spin or the subshell with the spin half electron, having the half spin or single electron. So on the other hand, the normal Zeeman effect occur within the system which are closed shell which has a closed shell of electrons. That is they are completely filled type of the atoms and their degeneracy in their states. Degeneracy in state. Degeneracy means that the splitting of the states are when there are the two different states of slightly different energy, two states of slightly different energy. Then it means that from where the degeneracy comes in the case of system with the closed shell of electron. So the system with or atom with a closed shell of the electron, the degeneracy comes in this system, arises in this system due to the lifting of orbitals. Lifting of orbitals by an external magnetic field. By an external magnetic field. It means that whenever we apply a magnetic field or when we place the atom within the magnetic field, atom with the closed shell of electron, there will be the lifting of orbitals. Lifting of orbitals means that there will arise a degeneracy in these atoms, that is the different orbital will get split in energy or there will be the lifting of orbitals in the presence of magnetic field. So in this way, when there is the splitting in the orbital because of the external field, and then the external field, here we use the external field of moderate strength. So this is another phenomenon that, as you know, that the splitting of orbitals also depends on the strength of the magnetic field, strength of applied magnetic field. So the strong field has its different impact, moderate field strength has its different effect, while the weak field has its different impact on the splitting of atom within the magnetic field. So here when we apply the magnetic field of moderate strength, magnetic field of moderate strength supports the normal Zeeman effect. It results in the normal Zeeman effect. It means that it results in the splitting of energy level and results in the equally spaced fine structures. Fine structures. So fine structure, what's mean by fine structures here? Here the fine structures means that splitting of lines, splitting of shell, or into the splitting of the line into the several line in the presence of magnetic field. Splitting of spectral line into the several lines in the presence of magnetic field is called as fine structures, and all these lines are equally spaced. This means that distance between these lines will be equal. They are equally spaced, will be equally spaced spectral line. So these fine structured line, the energy of each these fine structure state will be equals to mu m is equals to ml mu b into b. So each spectral line has energy which correspond to this one. So it means that for example, if there is the as we know that the normal Zeeman effect, in normal Zeeman effect we observe only the three spectral line due to the selection rule. Delta ml is equal to should be is equal to 0 or plus minus 1. So this selection rule allow the only observation of only three spectral lines. There is a splitting of line into the three fine structure line in the case of normal Zeeman effect. Now let's suppose that the original line has the frequency of mu naught. Then the line which is equals to the let's suppose this is the frequency of line 2. It is the middle one. And then the line which rise higher in energy than the original one, which can be represented by V1. So its frequency or its energy differ from the original one by an amount of mu b l ml into b plus lb, and that state which is lower in energy than the original states, its energy will be equals to the mu naught minus mu b into ml into b. Now let's suppose we have the two different states. This state correspond to L is equal to 0, and this state correspond to L is equal to 1. Now first we consider the case with, let's suppose, for when the B is equals to 0, that is in the absence of magnetic field. Absence of magnetic field, when there is no field. Then in this case there will be the transition from L is equals to 1 to L is equal to 0. So in this case we observe only a single line when there is no magnetic field. Now let's suppose when we apply the magnetic field, when there is the magnetic field greater than 0, it means that in the presence of magnetic field. Now what happens to these states? So for L is equal to 0, we know that ML also equals to 0. So this will be the state L is equal to 0, only we have the single state in the presence of magnetic field. But for L is equal to 1, we have three different value of ml are possible. For L is equal to 1, ml has three different values, and these will be equals to ml is equals to -1, ml is equal to 0, and this one is the ml is equal to +1. So in the presence of magnetic field, this line split into the three different lines. There are the three different orientations for L is equal to 1 are possible in the presence of magnetic field. Now there will be a transition will be from ml is equal to -1 to ml is equal to 0. There will be this one transition is possible, and this transition is also possible. So in the presence of magnetic field, we observe three different spectral lines. So as there are the three transitions, so we observe the three spectral line in the case of anomalous Zeeman effect instead of single line in the which we observe in the presence of magnetic field. So there is the splitting of spectral line in the presence of magnetic field. So this explains the normal Zeeman effect. So students, this was all about the origin of the Zeeman effect, and here we discussed the normal Zeeman effect. So in our next video we will discuss about the anomalous Zeeman effect. Thanks for watching. For more videos, please subscribe our channel.